Let's take a look at example 8. We're asked to describe the intervals on which the function is continuous. G of x is a piecewise defined function. It's defined as the sine of 1 over x when x is not equal to 0, and it's equal to 0 when x does equal to 0. So let's kind of pick this function apart and see what's going on here. So for the bulk of its domain, for all values of x, with the exception of when x is 0, the function is going to behave like the sine of 1 over x. Now, that's a composite function. And what we would know is the following. We know sine is defined for all real numbers. Therefore, this composite will be defined as long as 1 over x represents a real number. And that will be the case for all x different from 0. So that's the only value that would make this denominator equal to 0. And thankfully, that's the portion of the domain for which we're actually using this piece. So what that tells us is that as long as x is not equal to 0, then 1 over x will be defined, and therefore the sign of that defined number will also be defined. So right off the bat, we will know that g of x is continuous for all x is different from 0. So from negative infinity to 0, and then from 0 to infinity, it is continuous. The question, though, remains, well, what actually happens at x equals to 0? Is g of x continuous at 0? In other words, what we're asking is this question. Is the limit as x approaches to 0 of g of x equal to g of 0? Right, that's the definition of g being continuous at 0. The limit as x approaches to 0 of g of x would have to be equal to g of 0. Well, let's find out. So first of all, the value of g of 0, if we were to plug 0 into the function, remember when x equals to 0, the value for g of 0 is simply going to be 0. So we get the 0 output. And now what we have to investigate is the limit as x approaches 0 of g of x. Remember, when x is approaching 0, that means we can look at either the left-hand approach or the right-hand approach, but we're looking at values that are getting closer to 0, but are not equal to 0. And if we're approaching 0, that means that we're not 0, so that limit is going to involve this portion of g. So the limit as x approaches to g of 0, as x approaches to 0 of g of x, is the limit as x approaches to 0 of the sine of 1 over x. And we might recall that graph earlier, but that limit does not exist. The sine of 1 over x, as x gets closer to 0, this is a function that's going to oscillate infinitely often between negative 1 to 1. So because the limit does not exist, that means that g of x is not continuous at 0. So g of x is not continuous at x equals 0, and because there's no limit, it would actually be a non-removable discontinuity. So what we can determine, our final conclusion, remember the question says describe the intervals on which the function is continuous. Well, g will be continuous for all x different from 0. That's from negative infinity to 0, union 0 to infinity. Let's take a look at one more. Describe the intervals on which the following function is continuous. H of x here is defined for all x different from 0. It's x times the cosine of 1 over x. And when x is equal to 0, the value of 0 is going to be 0. So for the bulk of its domain, it's going to be this first piece right here. Let's investigate the continuity of x cosine of 1 over x by using our limit theorems. So first of all, this is the product of x times the cosine of something. That product will be continuous wherever the individual pieces are continuous. X itself, that's a polynomial. Polynomials are continuous everywhere, so this first piece is always good. That's continuous for all real numbers. So therefore, the product will now be continuous wherever this piece is continuous. And this is a composition. This is the composition of the function cosine with 1 over x. We know that the cosine is continuous for all real numbers. So as long as the inside function 1 over x produces a real number, then the cosine of 1 over x will also be continuous. The only place, or the only value of x, where 1 over x has an issue is when x equals to 0. But thankfully, that's not where we're using this function. So what that tells us is that this piece here is going to be well defined and will be continuous for all x not equal to 0. So immediately we already know that h of x is continuous for all x not equal to 0. The only thing that remains to check is, well, what actually happens at 0? Is h continuous at 0? Well, by definition of continuity at 0, we need to investigate what is the limit as x approaches to 0 of h of x. We need to see, is that going to be equal to the value of the function at 0? Okay, let's do the easy part first. If we plug in 0, we get out 0. So h of 0 is equal to 0. Let's investigate the limit. The limit as x approaches to 0 of h of x. This is the limit as we approach 0 from either the left side or the right side. But again, as you're approaching 0, you're getting closer and closer and closer to 0, but technically at that point you're not equal to 0. So when we're investigating the limit, we're going to be using this piece of the function. So the limit as x approaches to 0 of h of x is equal to the limit as x approaches to 0 of x times the cosine of 1 over x. And now there's several different ways you could try to do this limit. First of all, if you try to do the direct substitution, you would get 0 times cosine of 1 over 0, which would be an expression that is undefined because division by 0 is undefined. So direct substitution won't work on this. Okay. Well, what do we do next? If there's an analytical way to find the limit, that's the preferred approach. Couple analytical methods we've already discussed: factor and cancel. Can't do that here. Rationalizing a numerator and denominator, that doesn't come into play. Simplifying a complex fraction sometimes works. Using a well-known limit theorem, this isn't one of those. But squeeze theorem will work here. So we're actually going to use the squeeze theorem on this. If you don't think to do that, or if that doesn't cross your mind, you can always go back to one of our old school standbys and do either a numerical approach. So make a table of values where you see what happens as x gets closer to 0 from the left and as x gets closer to 0 from the right. Or you can even look at, let's say, the graph of this thing. So if you have your calculator, you could graph it, and the graph would also be able to kind of tell you what's going to happen here. However, since we can actually do this analytically, I'll use the squeeze theorem result. So first of all, one of the things that we know about a cosine function is always bounded between -1 and +1. That's kind of the largest output you could ever get, and the smallest output you could ever get from the cosine function. If I multiply this entire inequality by x, so we have -x is less than or equal to x cosine of 1 over x, which would be less than or equal to +x. So this function here is bounded by -x and +x. Let's investigate each of those limits as x approaches to 0. Well, the limit as x approaches to 0 of -x, that's simply going to be -0 or 0. And the limit as x approaches 0 of x is also going to be equal to 0. So because this function goes to 0, and the other function goes to 0, by the squeeze theorem, that means that this limit is also going to go to 0 as well. So what have we just shown? We showed that the limit as x approaches to 0 of h of x equals to 0. We showed that h of 0 is also equal to 0. And so h will be continuous at x equals to 0. So h is continuous for all x different from 0. And it's also continuous at x equals to 0. And that's everything. So h is continuous for all real numbers. So it's continuous from negative infinity to positive infinity. I think that the graph, especially of this function, can be very informative for a lot of us. So even though what's kind of happening here is because of that cosine of 1 over x, kind of similar to the example we saw last time where we had like sine of 1 over x, we do get some kind of oscillations that are going to take place. But what happens is as x gets close to 0, we have kind of like this coefficient out in front, which you can almost kind of think of almost like as like an amplitude kind of thing, where as x gets close to 0, this outside factor gets small, and so what you have is kind of like a series of like damped oscillations. And you can graph this with a graphing applet to see what's going to happen here. But as you approach 0, what's happening? So the oscillations will get wildly. I mean, it'll get really large. But then as you get closer to 0, it starts to get dampened like this. And the same thing happens on the other side. Now, one of the issues with this function, because you can't divide by 0, at that point, that would typically be an open circle, because it would be undefined at 0. But yet, what we do is we define the value of x equal to 0 to precisely be equal to 0, which is the limit. And then that fills in that point and gives us a function that is continuous then for all real numbers. One of the last things we'll close this section with is the intermediate value theorem. A lot of times you'll hear me just kind of abbreviate it to IVT. And this is an existence type theorem. Let's suppose that f of x is continuous on the closed interval a to b. So we have continuity on the closed interval a to b with f of a different from f of b. And let's suppose that k is any number between the value f of a and f of b. Then there exists at least one number c in AB such that f of c is equal to k. So if we have a continuous function on a closed interval, then the intermediate value theorem applies, and it says that the function will take on every value in the interval a to b that's between f of a and f of b. Intuitively, what's kind of happening here, if you want to try to get a feel for what this theorem is really telling us, let's suppose we have a function. Here's a, here's b. The function is continuous on this interval. I'm going to put f of a here, and let me put f of b there. So the function starts here. It's going to end up here. And who knows what it's going to do in between, but the function is continuous. And if you go back to our intuitive definition of continuity, that means that the function is not going to have any breaks or gaps or jumps in its graph between a and b. So what the intermediate value theorem tells us is that if I pick any number, let's call it k, that's in between f of a and f of b, let's say k is right here, okay, that there has to be some point and I'm going to call that point C. Furthermore, it says that there's at least one C. There could be more than one, but there'll be at least one value C in between A and B such that f of C equals to k. That's what the intermediate value theorem says. And it makes sense because if that wasn't the case, then there'd have to be like a break or a jump or something funky would have to go on for the function values to miss that value k. If f is going from f of a to f of b on the interval, then essentially what it's saying is it has to hit every point or every value on the way there. So the IVT guarantees the existence of this value c, or at least one value c. It doesn't tell us how many there are, nor does it necessarily tell us how to find them, though. So this is, in mathematics, what we call an existence-type theorem. Okay. One of the biggest uses of the intermediate value theorem is to find zeros of functions on closed intervals. Okay. If we look at just kind of this graph, kind of like what we were saying a moment ago, this function f is continuous on the interval a to b. So pick any value between f of a and f of b you would like. Here they pick the value k. And if I draw the horizontal line y equals to k, here in particular there's 3 different places where the function will have a value equal to k. They label them c1, c2, and c3, but we're certainly guaranteed at least one place. Notice that this result does not hold if the function is discontinuous on the closed interval. So here, if you look at this particular function on the closed interval a to b, it has a jump discontinuity at, let me call this d. So at d, the function has a jump discontinuity, and in particular, there's places where this function is going to miss a whole slew or a whole range of values because of that jump discontinuity. So be aware that in order to apply the intermediate value theorem, it's the property of a continuous function on a closed interval. Let's use example 9 to show that the function f of x equals x cubed plus 2x minus 1 has a 0 in the interval 0 to 1. Okay. So let's be very thorough with this. So first of all, they tell us to use the intermediate value theorem, but it's important for us to understand why the intermediate value theorem applies. First of all, f of x, this function here is a polynomial. And one of the things that we know about polynomials is that polynomials are continuous everywhere. Okay. In particular, that means that they'll be continuous on any subset, closed subset of the real line. I shouldn't say closed. Any connected set of the real line. Therefore, it'll be continuous on this closed interval. So because we have a polynomial, we know it's continuous, and therefore it's continuous on 0 to 1. And that means that the IVT will apply here. So it's not just a matter of them telling us to use it. We actually know that we're able to use it because this function is continuous on the closed interval. The next thing we're going to do is let's look at the value of f at the endpoints. If we plug 0 into this function, we get 0 cubed plus 2 times 0 minus 1, which is negative 1. If we plug in the right endpoint, which is 1, we get 1 cubed plus 2 times 1 minus 1. This is going to be equal to positive 2. Because 0 is in between negative 1 and 2, this is f of 0 is less than k. I'll just put 0, which is less than f of 1. That means that there will be a point. So there exists, by the intermediate value theorem, a value c in the open interval 0 to 1 such that f of c would be equal to 0. So at the left endpoint, the function was positive. At the right endpoint, the function was negative. It went from negative to positive. The only way that you can go from negative to positive, if you have a continuous function, is that at some point you would have to pass through 0. And that's nice because now we know that this function does have a 0 in between 0 and 1. If you were asked to actually solve for that solution by hand, that might be somewhat of a difficult task for us right now, based upon the type of math that we know. But we'll come to later on methods that'll help us to solve that.